Hello there, students. Today's lesson is coming from Chapter 1. It is Section 8, Interpreting Graphs of Functions. And just as a heads-up reminder, this is the last section of this chapter, so you should be expecting an exam soon, and that information can be found on your assignment sheet. But anyway, today we're going to talk about different ways that we can interpret graphs of functions. So one of the first things that we're going to be talking about is intercepts. And intercepts, there's two types of intercepts. There's what we call an x-intercept and also what we call a y-intercept. And just like their name indicates, an x-intercept is the place on the graph where on the coordinate plane where the graph will cross the x-axis, and likewise the y-intercept is the place on the graph where the graph will cross the y-axis. So here we have in example 1, the graph shows the height y of an object as a function of time x. Identify the function as linear or nonlinear, and then estimate and interpret the intercept. So first of all, is the function linear or nonlinear? And just as the words linear imply, linear means that it looks like a line. And so since this graph is actually a curve, therefore not a line, it is actually going to be called nonlinear. So the first thing we wanted to do is indicate, I'm going to indicate it by using my highlighter here. Instead of linear, we're going to circle it is non-linear. Let me try to find a lighter color there. Non-linear, because it is not a line. Had it been a line, we would say that it was linear. All right, so the next part is asking us to estimate and then interpret the intercepts. So first we're going to go to the estimate. Okay, now we're going to do this for the x-coordinate, or sorry, the x-intercept. And we're also going to do it for the y-intercept. So the x-intercept is basically where the graph, the blue part, actually crosses the x-axis. So we can see here that it's crossing the x-axis almost at 7. It's probably a little bit above 7. But we are going to estimate it to be, and again, this is a graph that I drew from the book, so if you actually want to see a better graph of it, it is on page 56. And we're going to go ahead and go with what the book says. When I look at my graph, it doesn't look like this is 7.4. I would probably call it more like a 7.2. But that's probably because my graph is a little off. But if you look at the graph in the book, it's crossing at approximately 7.4. So what we do is we recognize that the x-coordinate of the intercept is roughly 7.4 and the y-coordinate is 0. So for the x-intercept, we have that it's 7.40. All right, so then before we get to the y-intercept, we also have to not only estimate it, but interpret what it means. And we know from the graph that the x-intercept represents time, it's a function of time, and that the y-coordinate represents the height. So since the x-coordinate is time, and time, according to our graph, is measured in seconds, it means that there has been 7.4 seconds that have elapsed. And then the 0 indicates that that's when the object has reached the ground, because 0 height means that it's on the ground, and so forth. So I'm not going to write all that out because I'm not going to have enough space. But basically this means that the object struck the ground after about 7.4 seconds. So if you want to write that down, that's fine. The object struck the ground after 7.4 seconds. So then next we are going to go to the y-intercept. I'm going to write down here y-intercept. And with the y-intercept, we're actually doing the opposite of what the x-intercept was. We're looking for the place where the graph crosses the y-axis. So you can see here, a little below the 20 mark is where the y-intercept is. But like we know from before, that when you graph a point, you always start at the origin and then you move left or right on the x-axis first. And since we're not moving anywhere on the x-axis, the x-coordinate of the y-intercept is 0. And then the y-coordinate would be 19 point something. And we're going to, again, look at the book here because we don't want to be faulty. So see, that's exactly what I was concerned about. So on the y-axis, again, if you look at your graph in your textbook, you'll see a better picture. It's actually, the line is actually crossing more in the middle here. And since we are going by tens, they're going to estimate that at 15. Even though in my case it looks more like 19 or 18 or 19, and according to the textbook it looks like a 15. So again, to stay consistent, we're going to say 15 here, and that would be measured in meters. That would be 15 meters. All right, so the y-intercept is said to be x-coordinate 0, y-coordinate 15. And I want you to notice something, and this is true all the time. Whenever you find the x-intercept, it is true that the y-coordinate will always be 0. And whenever you find the y-intercept, it is true that the x-coordinate will always be 0. Just like a little factoid there for you as you go forward. Now, the last part we have to do for this example is to interpret what that intercept means. And again, we know that 0 is the x-coordinate, and that's measured in time. So this would imply 0 seconds have elapsed. And then this is saying that it's 15 meters. That means that at 0 seconds, the object was already at 15 meters of height. All right? So again, we're going to, I'm not going to write it all out, but I will say that again so that you can write it down in your notes. This means, the y-intercept here, 0, 15, means that the object started at an initial height of 15 meters above the ground. So time equal to 0 means that time hasn't started yet, and so it was already at 15 meters, which means that it was an initial height of 15 meters. And as you can see from the graph, after about maybe 2 seconds, it was roughly at about almost 60 meters. It looks like at around 3.5 seconds, it reached its highest point, a little bit above 70 meters. Or sorry, yes, we're going by tens. So 70 meters, and then it starts coming back down, and then eventually hits the ground again. So anywho, that is how we interpret x and y intercepts and how we describe linear or nonlinear. So we have another example for you here. Now again, the graph here is found in your textbook on page 56 if you want a cleaner graph to look at. Then we're going to move on to symmetry, and what we call line symmetry. And so here I have a definition for you of line symmetry. And line symmetry is when each half of the graph on either side of the y-axis, or it doesn't have to be the y-axis, it could be some other vertical line, matches exactly. It's kind of like if I were to draw a vertical line, the two sides of the graph would be like mirror images of each other. I would be able to fold the graph along that line and the two sides would match exactly. So that's kind of what line symmetry is. And so here we have an example to kind of show you what that would look like. And it says an object is launched. The graph shows the height y of the object as a function of time x. So it's a lot like our previous example, but it's not the exact same one, but it looks a lot like it. Describe and interpret any symmetry. So again, if you look here, if I were to draw a vertical line, and I'm going to look at this and think that the middle is roughly right here at about 3.5. So if I were to put my ruler, my straight edge, trying to line it up here. Alrighty, I hope I line this up straight. There I go. Alright, so I have this like dashed line here. Now again, my graph is not perfect. If you look at the textbook, you will see a much better graph. It's on page 57 in this case. But basically this is roughly where I find that the middle is. It's where the graph kind of goes up and then it starts coming back down. And again, if I were to fold this graph on this line, they would be mirror images of each other. They would match exactly as it says here in the definition. So this would represent a vertical line that's not the same thing as the y-axis. Sometimes you'll find that these graphs, the middle, if you will, is on the y-axis. In this case, it's not the y-axis. It's a different vertical line. but just wanted to be really clear here to emphasize that you can only really have this type of symmetry when it's a vertical line. We're not looking for horizontal lines that have matching halves. We're looking for vertical lines that have matching halves. So again, line symmetry is when each half of the graph on either side of the y-axis, or in this case, a vertical line, match exactly. So that's our line symmetry. And since this vertical line is going through x equals 3.5, x equals 3.5 is what we would call the line of symmetry. Okay? So what does that mean? It says to interpret. So when you interpret something, you're supposed to give the meaning. Well, in this case, what it means, because this is an object, again, that has been launched, it means that from the time that the object was launched to when it came back down, okay, it took the same amount of time to get to the highest point as it did to get back to the ground, okay? So again, I will say that again for you so you can write it down in your notes. But again, I'm not going to write it out because it's going to take too long and it's going to not have enough space. So, in the context of the situation, the symmetry of the graph tells you that the time it took the object to go up is equal to the time that it took the object to come down. So the same time that it took the object to get up to the highest point is the same, 3.5 seconds, is the same 3.5 seconds that it took for the object to come back down to the ground. Alrighty, so that's symmetry for you. Not very complicated, but there you go. And now what we want you to do is we want you to go back to the do-it-yourself number 1 question, and we want you to describe and interpret any symmetry exhibited by that graph. All right. And then we're going to go through 4 different, I don't know what you want to call them, characteristics of graphs. And I didn't, in your book, they kind of have it in a chart, like a 2x2 chart with 4 options. But I didn't have enough board space to put all 4 of them on one slide. So I'm going to have to do them one at a time. If you want to write them in your notes as a grid, and you can see the grid on page 57 of your textbook, then you're welcome to do that. But in my case, I didn't have enough space, so I did one slide at a time. So please don't hate me and just forgive me for that, okay? So we're going to be talking about extrema and end behavior. So here we begin with our first graph, and we're talking about whether or not a function is positive or negative. So a function is positive where its graph lies above the x-axis, and it's considered to be negative where the graph lies below the x-axis. So here I have a graph for you. You can see that at these very points here, the graph, let's pick a different color there because you can't even see that. Maybe you can see that green there. There are 3 points here that I'm highlighting in green. These points are neither positive or negative. They're actually 0. That's where the function equals 0, and 0 is neither positive or negative, so we just call it 0. It's neutral. But you can see that everything above the x-axis, so this piece here, and all the stuff between these 2 green points is positive because it's above the x-axis. And then we have the negative part, which is where it drops below the x-axis. So from between these 2 green points, it's all negative. And then after this green point, it's all negative. So just so that we're aware, that's what it means to be positive or negative. And then we have increasing and decreasing. A function is increasing where the graph goes up and decreasing where the graph goes down when you look at the graph from left to right. Now, a lot of times people confuse this with positive and negative. They think that increasing is the same thing as positive and decreasing is the same thing as negative, but that's not the case. I want to show you that when you're decreasing, you're looking at the graph, you read graphs from left to right just like you would read a book. So if I were to start up here somewhere where this tip of this arrow is, and if I were to try to move myself in this direction, going left to right, I would find myself going down, 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 down. And then right when I got about here, I would find myself starting to go back up, 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 up. And then when I got to right here, I'd start going down, 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 down. So you can see that from here, so from roughly around this x value all the way to that x value, between these 2 x values, the function is increasing. And from negative infinity up until this x value, it's decreasing. And over here, Yes, decreasing and also decreasing here. So, just to be clear, when you go to the previous graph, notice how the positive part does not dip below the x-axis. But in this case, this is not even positive, but it's dipping below. And in the case of the increasing, which we would think, oh, it's positive. No, there is a part of the pink graph that is below the x-axis. This is still considered negative. It's a negative function values. But even though the function values are negative, they are getting bigger and bigger, which is what we mean by increasing. It doesn't mean that it's negative or positive, it just means that it's getting bigger and bigger. So if it was negative, it's getting bigger as you go along the graph. So when we talk about function increasing, decreasing, they're going to ask you, where is the function increasing, where is it decreasing, and we're going to use the x-axis to say that. So for example, let's say that I put here -5, and over here I put 2. This is just arbitrary. Then I would say that the function is increasing between x equals -5 and 2. Okay? So between this x value, so you see how the x value is -5, and that's where it starts increasing all the way up to when x is 2. But the function is decreasing from 2 and on, or from 2 to positive infinity. Okay? Or another way of saying that is to just say from x is greater than 2. Once the x values are bigger than 2, everything this direction is decreasing again. And also we know that over here, for anything that's less than -5, it's also decreasing. So we'll have to come back and we'll have to do increasing, decreasing in one of the examples in the future here. But that's kind of what increasing and decreasing is. And then we have extrema, okay? And extrema is basically another way of saying extremes, but it's plural. So there's two types of extremes. There's the extreme maximum and the extreme minimum. So here we go. The points shown, and I have 2 points shown here, are the locations of relatively high or low function values called extrema. Point A, here we go, point A, is what we call a relative minimum, since no other nearby points have a lesser y-coordinate. And when they say that, this is an important word, that no other nearby. Let's go back to nearby. Important word, okay? Because obviously what I want to show you with point A is, here is the y value, right there. Bam. Why does it keep doing that? Sorry. There we go. This is my y value. Now let's suppose that this y value is -10. I mean, we don't really care, but it's a y value. Now what we're saying is, we're not saying that this is the lowest point on the graph forever. I mean, clearly we can find that there's a point over here, and the y-coordinate of this point is lower than the -10. So this point is obviously smaller, more of a minimum than this point. So you have to understand what they mean by the word relative. Okay, relative means that in that general area, it is the lowest point. So if I were to take maybe a magnifying glass, and I'm just looking at these points right here, when I look at just those points, this is the lowest point in this circle. And likewise, we have this guy over here. And point B is a relative maximum because it's the highest point in this area. Since no other nearby points, nearby, again, the key word there, nearby points, all right, no other nearby points have a greater y-coordinate. So in this circle, this value, this point has the highest y value, even though we know that later on there is a higher y value up here, but in this general vicinity, that's the highest point, okay? So sometimes we call these hills and valleys. You know, this is like a hill, a valley. But relative maxes are when you have hills, and relative mins are when you have valleys. So we're going to be asked to find max and mins in our graphs as well. So hopefully that makes sense to you now. Okay, and the last topic that we have before our last example is end behavior, okay? So end behavior describes the values of a function at the positive and negative extremes in its domain. This is not the same thing as max and min. I am not looking for the valley and the hill or the min and the max, okay? I'm trying to see what happens when the domain values, okay, domain values are at extremes. And this can become somewhat complicated because you'll remember before we talked about domain and range, and domain is all about the x. So when we talk about end behavior, it's describing the values of the function. That's literally what the y values are. The value of the function is the y value. Okay, the domain of the function is the x value. So what this is telling us that we want to describe what is happening with the y values when the x values have positive and negative extremes. So just for the record, we're talking about when the x-axis goes extremely positive, this is the positive side, or extremely negative. What happens to the y values when the x values go to each extreme? Okay, so let me tell you what I mean by that. So here we have the description here. As you move left, okay, so if you start here at the origin and you move to the left, okay, this direction, you're moving to the left, the graph is going up. So, and again, what does that mean? Is it going up? Okay, when you're here, where's the y value? Here's my y value. When I move to the left, now here's my y value. When I move further to the left, there's my y value. And I go further left, there's my y value. It is very strange because as I go to the left, my y values are actually going down. But this is not what this end behavior is talking about. Think end behavior, the end of the graph. This is not the end of the graph. This is like the middle. What we see right here is like the middle of the graph. We're talking about what happens in the end, like the end times, okay? What happens at the end of the day? Okay, so as you keep moving to the left, eventually you'll get past all of this hill and valley stuff, and you will start to see that the graph, in fact, is going up. And this arrow indicates that it's going up forever. So that's why we say that as x decreases, okay, so the x values are getting smaller, because then this is the negative x direction, so they're getting smaller and smaller and smaller and smaller. They're getting more and more and more negative, so smaller and smaller and smaller. So as the x values get decreased, the y value is actually increasing. Okay, that's happening there. All right, and in this graph, or sorry, not the same graph, but on this side, it says as you move to the right, and so if we did the exact same thing, if we started moving in this direction, okay, to the right, the graph goes down. And again, initially that seems like a lie, because initially the graph is going up, okay? But as you continue to keep going to the right, it will start to come down and eventually just go down, 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 down forever and forever. So as x increases, again, positive direction, and now the x is getting bigger, the y value is decreasing. These y are getting negative, negative, negative. All right, now this can be flipped around, so this is not always the case. Sometimes you can have a graph that looks like this. Okay, and in this case, as x gets small, y gets small. And as x gets big, the y values get big. It's kind of the opposite of what that one's doing, because in this case, you think of, I always think of arms, okay, so you're like this. When you're like this, if it becomes negative, those arms can flip like this, okay? So it's important that you not just always write down exactly what you see here, because it depends. You have to look at the graph. Is it going up or is it going down? Is x getting smaller or is x getting bigger? And then describe the end behavior, okay? So we're going to do that right now with this example. I'm going to help you kind of, we have a graph over here. And it says that this graph is U.S. retail sales of video games from the years 2000 to 2009, and they can be modeled by the function graph at the right. Estimate and interpret where the function is positive, negative, increasing, decreasing. They want the x coordinates of all the relative extrema and the end behavior of the graph. So we have to start small here. Again, I really need you to to be listening and pause if you need to and write things down, because I'm not going to have enough space to write all that stuff down. But I am going to go to the graph and kind of show you what is going on here. So first they want to know whether the function is positive or negative. So we said before that the function is positive when it's above the x-axis. So from here, all of this part of the graph is above the x-axis. So the graph is positive from roughly like -1 all the way to almost 10 point something, 10.3. All right? So between about, and again to be clear, this graph can be found on page 58 in your textbook, and they have a more accurate looking graph. So it's positive between, according to them, -0.6. So we've got positive, I'm not sure you can actually read that, so I'll put a different color here. We got, hello, okay. We have positive function from x equals -0.6 and roughly 10.4. That's where the graph is positive. So then that would mean that the graph is negative when x is then smaller than -0.6, because this is -0.6, so it's positive this way, and it would be negative in front. So it basically less than -0.6. And since over here 10.4 is where it ends the positiveness, then for x is greater than 10.4, it would also be negative. All right, so that's for positive, negative. And then what does this mean? Because it says to estimate and also interpret. So this means that there were positive sales between about 2000 and 2010, but the model predicts that there will be negative sales after about 2010, indicating the unlikely collapse of the industry, because it doesn't appear that this function is going to come back up. It's going to keep going down in negative. So negative sales eventually, if they don't do something about it, they're just going to go out of business. Okay? But again, they had positive sales from the year 2000 all the way to 2010. But a little bit after 2010, they're going to have to start doing something with their company, or they're going to go bankrupt. All right. Then it wants to know where is the function increasing and decreasing. And again, remember that it's not the same thing as positive and negative. So increasing and decreasing. That's when you read the graph from left to right, and you try to see where it's going up and where it's going down. So we can kind of trace this graph, and it's increasing here. And then you can see that it kind of has a dip, and then it starts increasing again, and then it has a dip. So in these two places, it's increasing, and then right about here, it's decreasing and decreasing over here. Okay, this value right here is a little bit past the 8. This value right here is between 1 and 2. So again, going back to the textbook to make sure we have the exact values that they're having. Increasing, we're going to go with 1.5. So this value right here is roughly 1.5. So it's increasing for x's less than 1. I can tell you this is why I was worried about having. So it's increasing for x's less than 1.5. So from everything that's over here, less than 1.5. And then it's also increasing between 2 and 3. I'm sorry, 3 and 8. So this value right here on my graph kind of looks like 4. But again, the book is claiming that this is 3 and then 8. So also between x equals 3 and x equals 8. Okay, increasing. So then the decreasing is going to be from 1.5 to 3 and from 8 on. So it's going to decrease x greater than 8. So once you get to the 8, everything past 8, bigger than 8, is going to be decreasing. And also between x equals 1.5 and x equals 3. All right. So that's the values of increasing and decreasing. But what does that mean? This means that sales increased from about the year 2000 to 2002, and then decreased from 2002 to 2003, and then increased from 2003 to 2008, and then have been decreasing since 2008. And again, those numbers based on, these are the years since 2000.